Today we'll have a week 2 summary.
Yes, yes, we will be having Week-2 summary. Give me a minute, okay? I'll just share
Okay,
my screen.
sure.
Yeah. Okay, is my screen visible?
Yes, ma'am.
Yes, ma'am. Is the writing visible? Whatever I'm
Yes. Yes.
writing in the. Okay. Okay, all right. So in this week, the contents is on the growth rate of functions, and we'll look into some searching and sorting algorithms. So mostly what this growth rate of functions is, so we'll start with growth rate of functions and the complexity analysis. So what happens is in complexity analysis, so we need, suppose we are given a couple of algorithms, okay? We are having these two, three algorithms. We know for one particular solving a problem, we have two, three different types of algorithms. Like for example, I'll just begin with one simple example. Suppose we are asked to multiply two numbers, okay? So we are asked to, let's say, addition of two numbers. Suppose we have 3 plus 4, we have to do. We can use some function, we just remember, and we can just say that 3 plus 4 is 7, right? And there is another way out is we can just count 3 and then 4. Now, suppose we are asked to add two numbers, 1, 3, 5, 8, and 2, 0, 4, 9. Okay, we are asked to add these two numbers. So one of these ways is we can just start adding the last two digits. This is 17. Then we have 5 plus 5 is 10. Then 4. And then we have this 3, 3, 4, 0, 7. We can do this, right? This is one method. Then there is another method is we just put 1358 dots, and then we put 2049 dots, and then we start counting each one of them, right? So both of the methods give us the same thing. So both of them are algorithms only to solve the problem. And the problem is we want to add these two numbers, right? So what our algorithms is doing is our algorithms are just counting the total. Both of them are doing the same thing. But the thing is which one is faster? We want to know which can run in a better time, which takes less space to compute, which runs in faster time, and all of that. We want to analyze both of this. We want to compare these methods. Which of these is a preferable method? Okay. So that is what the idea behind the complexity is. So the complexity of an algorithm is basically we want to assign some function to our algorithm which will help us, which will be like giving us an estimate on how much time or how much space the algorithm takes to solve the problem. Okay, so that is what complexity is, and complexity analysis is more like how exactly we will be comparing two algorithms. This, so we will be representing the running time of an algorithm as a function, and we want to compute like this running time is is running as this function, on this function, that algorithm is running using that function. So how much time this running time, how do we compare these two? That is what we will look into in the complexity analysis. Okay, like for example, for this addition problem, again coming back to this addition problem, what the algorithm, first algorithm was taking is, it is basically how many digits are there. Like it is a function of the number of digits, right? So we take the function of these digits, and we just have to add two single digited numbers, right? So this is dependent on the time taken to add two single digit numbers plus the total time or maximum three single digit numbers, and the total time to the total number of digits in this numbers, right? The maximum number of digits in these numbers. So that is a function on which the first algorithm was depending on. The second algorithm, it was depending on the total sum, like whatever, how many points we will be needing, right? So we have to, like, whatever is the value, like we will be needing 1358 dots, then we need 2049 dots, and then again we need to count all of these dots and something of that sort. Okay, so that function is depending on the numbers. So obviously, because our number of digits is less as compared to the total number of dots we will be putting, we will our first algorithm is faster and preferable as compared to the second algorithm, right? So something like that we will be doing for the complexity analysis of complicated functions also. So what we will do is, suppose our algorithm, first algorithm takes some f of n time. Let's say our input, we have whatever the input to our program is, has a size of n. Suppose we are inserting n numbers. Okay, so that size of the input is basically n. We are inputting n numbers. And now what we want to do is find the sum of these n numbers. So whatever my algorithm will take is, suppose we assume that addition takes just unit amount of time, then what happens? I add the first number and the second number. Suppose I have n numbers here, right? So I will add the first number and the second number. I will add this total with the third number. I will add this total with the fourth number, and I'll keep on doing this. Okay, so the total time will depend on the total number of inputs, the total number of values that we have inserted, right? So we have given as input, right? So that is why our function will depend on n, right? Similarly, suppose, so this is what I meant by saying that our algorithm, let's say our algorithm is a some function of n. Okay, the first algorithm is some function of n. Similarly, what is the second algorithm? Suppose we are having one algorithm which takes f1, some function f of n, okay, which runs in time f of n. Okay, similarly, there is another algorithm which runs in time g of n. Okay, so now how do we compare between these two? We have two functions and we want to compare between these two functions. So that is where the order notation comes in. Okay, so I'll come to that little bit. So this is the growth rate of functions thing. So this is where the order notation comes in. So what we want is, we want to see how fast these functions are growing. So with increasing n, what happens to the function? Let's say my function in this graph in the xy axis, my f of n is growing in some way. Okay, this is my f of n. Now what is happening is, my g of n is growing in some other way. Something like this it is happening. Okay. So what happens is, there is some point. Let's say this is my g of n. Okay. So now notice that after certain value of n, like for some certain value, let's say this is some value c. For some value n is equal to c, my g of n is equal to f of n. But for every n greater than c, g of n is greater than f of n. Okay. So if such a scenario occurs, we say that f of n is equal to order of g of n. Okay. So what it means is, when my n keeps on increasing for very, very large values of n, my f of n will always be less than g of n. Okay, this is the way we denote this order notations. It's called as the asymptotic complexity analysis, and this is how we compare between two functions. Suppose we have one function is f of n, the other function is g of n, and if I'm saying that f of n is order of g of n, that means that my f of n, the value for f of n for a very large number, the value of f of n will be less than equal to the value of g of n. Okay, so now what is the opposite? Suppose here, for some value n, very, very large value of n, my g of n will be strictly greater than f of n, right? So not strictly greater, it can be greater than equal to f of n, right? So under that scenario, we use the omega notation. So here, if for some very, very large value of n, my g of n is greater than equal to f of n, this means that my g of n is equal to omega of f of n. Okay, omega means it's a lower bound. So my value for g of n will be greater than f of n, greater than equal to f of n. Okay, and order means it is upper bounded. So there is a upper bound, so my value will be less than the other one. Okay, so that is the difference between order and omega. So now when we are comparing between two functions, let's say that we have one function given here, f of n is equal to 2n square plus 2n plus 3. And then there is g of n, which is saying that let's say it is 3n square plus 3n plus 3. So now what will happen? What will happen is for some particular value of n square, I agree with you that if it's for some value of n, my g of n will have greater values for f of n. But when you go towards infinity, when n tends towards infinity, this constants doesn't really hold that much of importance. Okay. So for theoretical purposes, when we are analyzing the complexity, what is called as the asymptotic complexity, for analysis purposes, we will be ignoring all the constant factors and lower order factors. So for this particular function, what are the lower orders? So this is the lower order. This is the lower order, right? So the highest order of n is only this 2n squared, right? So my f of n, we will be ignoring all of these lower orders, we will ignore all the constant values and we will say that f of n is n squared. So whatever will be the asymptotic complexity for f of n equals to 2n squared plus 2n plus 3. So the asymptotic complexity of n squared will also be the same. Let's say I'm just going to mark it as f dash of n, not f dash, let's say f2 of n, just to distinguish between these two functions. Okay. So whatever will be the asymptotic complexity of 2n square plus 2n plus 3, the same will be the asymptotic complexity for n squared also. Okay. Now, similarly for g of n, what will be the asymptotic complexity? The asymptotic complexity of this entire function will also be the same as the asymptotic complexity of n squared. Okay. So, basically what it means is f of n is equal to g of n. Okay. Just curious, am I still connected? Can somebody confirm this? I just heard
Yes,
some.
ma'am. Yes, ma'am.
Yes, ma'am.
Okay. Yeah. Okay. So, under such
But
scenario, sorry, yeah,
yeah, could you explain asymptotic complexity?
asymptotic complexity is basically the name. Okay, it's just called asymptotic complexity. That's all. It's not something big deal. Complexity is what we are discussing right now. Complexity means how complex a function is, how like how complex an algorithm is. So the running time of the algorithm, how it runs along some particular function, right? So whatever input we are giving, it depends on this that the size of the input. So let's say we have an input something, and my algorithm runs in some function of that input. Okay, so now we want to find the how like how this function is increasing. Okay, so suppose we say that my function f of n is 2n squared plus 2n plus 3. What this means is my algorithm runs in this particular time. Suppose I give n equals to 5 values, then my algorithm will take some constant times this f of n. F of n is the f of n will be equals to f of 5. Okay. So if you solve f of 5, which is 25 to 50 plus 10, 60 plus 3, 60.
63.
Yeah, sorry. So it is 63, so it will take some 63 units of time. Okay, so that is what as this f of n means. Okay, so like suppose my n is equal to 10, then what will be f of n? It will be equal to f of 10. We can count f of 10, it will be 223. Okay, so something like that. So whenever my n value changes, it depends on the size of the input. So depending on the size of the input, the time taken by my algorithm will also keep on changing. So all I'm saying is the running time of my algorithm depends on this function. This much is clear, right? Or any
And
doubts still?
from this running time f of n, it is
Yes.
the number of computations the function has to perform, right? For an input size n.
Yes. So isn't it like, see,
Number of operations.
exactly. If you are performing X operations and every operation is taking unit amount of time, that means the total time taken is the number of operations times 1, right? So that will be equal to 2n squared plus 2n plus 3, which is basically equal to the number of operations.
Yeah, proportional to it, the time.
Exactly. Yeah. So what is he saying is the number of operations we are assuming that so this is basically what f of n here represents is the number of unit operations that the algorithm requires. Okay. So this is the total number of operations that the algorithm is performing, and we are assuming every operation is taking like unit of amount of time or some constant amount of time. So we are saying that the time taken by this algorithm will be proportional to this function. That's clear, right? Hello?
Yes, ma'am.
Any other doubts till now? Okay, so if you don't have any doubts, you can like ask me at any point of time. Okay, so if you don't have any doubts, so let's now go to the notation thing. What this notation is basically, we are comparing two algorithms. We are given one algorithm, A1, and we have another algorithm. The running time for this algorithm is proportional to it runs along this f of n, which is let's say it's 2n squared plus 3n plus 4. And the running time for the second algorithm is g of n, which runs along the function 3n squared plus 3n plus, okay. Okay, so now what we have these two algorithms, and I want to compare these two algorithms. Okay, hello. Let's say there is another algorithm. Let's say there is another algorithm which is running along the function h of n is equal to n cube plus 3n squared plus 2. Let's say just n squared. N cube plus n squared plus n squared plus n plus 1. Okay, so this is my third algorithm. So we are having three different algorithms to solve one problem. Okay, and now we want to compare these three algorithms, and we want to say which algorithm is the fastest and the best algorithm. Okay, so what we will do is we will be using what is called as asymptotic complexity. Asymptotic complexity is just the name of this analysis. Okay, the kind of analysis that we are doing. Hello? Somebody was saying something. Hello? Hello?
Ma'am,
Yes, ma'am.
maybe someone's mic was on.
I'm sorry?
Maybe
Not all.
someone has not muted or someone has not muted.
Okay, okay. Okay, so we want to compare these three different algorithms, and how do we compare? So basically we will be comparing these functions, right? For some particular value of n, notice that initially, let's say if we take n equals to 1, if n is equal to 1, this value will be the least. A3 will be the least, right? The value, the time, the proportion of the time or the amount of time required for A3 to run should be the least, right? As compared to A1 and A2. But if we keep on increasing n slowly, okay, and it keeps on increasing. Okay, for a very large value of n, what will happen? My A3 will always have a larger time as compared to A1 and A2. Do you agree with that?
Yes, ma'am.
Why
Can you
is
Yes,
repeat
ma'am.
this, ma'am?
sorry?
Can you repeat this? What you have said?
What I'm saying is, for some n is equal to 1, which function will run, which algorithm will run the fastest?
A3.
A3. For n is equal to 2, which algorithm will run the fastest? I'm not asking you, you don't have to calculate now. Suppose I keep on increasing n. Now n is equal to 10, n is equal to 15. Suppose I keep on increasing n to n is equal to 10,000. Okay, for n is equal to 10,000, which of these three algorithms will run the, which of these algorithms will take the most amount of time, highest amount of time? It will not be the
A3.
fastest one.
A3.
It will be A3, right? So, what I'm trying to say is, at some point of time, the running time required for A3 crosses the time required for A1 and A2, right? This is, let's say A1 and A2 are somewhere around here, but A3 will just cross A1 and A2 and it will take higher amount of time. Do you agree with me? At some point of time, let's say
Yes,
this is
ma'am.
4 hours.
Yes, ma'am.
For some value of n equals to c, after that A3 will always have a higher amount of time as compared to A1 and A2. Right? So, what we are saying is A1, the function required by A1, which is f of n will be order of h of n. This is just a notation, okay? It's not nothing big. For some point of time, for some value of n is equal to c, for every value of n greater than this particular c, okay? For every n, when n goes greater than c, what happens is h of n is always greater than equal to f of n, right?
Yes, ma'am.
That is
Yes,
why
ma'am.
we say that we just use this new notation f of n is equal to order of h of n. This is denoted by a capital O. Okay?
And so this basically means that algorithm takes maximum time proportional to h of n, right?
Yes. Yes. What my algorithm A1 will never take time greater than h of n. Whatever will be the time taken by h of n, my algorithm will take less or equal to time than that.
H of n is the worst
Ma'am,
case.
Sorry?
H of n is the worst case time.
Exactly. H of n is the worst case time.
Ma'am, but doesn't this depend on the number of operations? Like you just gave us an example in the first, where n is equal to 1, A3 is
Yes.
actually the shortest one, right? And then
Agree.
as n grows, it becomes, suppose we have a list which has only one element. So we have n is
Yeah.
equal to 1. Then in that
Yeah.
case, A3 would be the most efficient way to go about it.
Yes, I agree with you. A3 would be the most efficient way to go about it. But when we are comparing algorithms, we want to compare it for general inputs. We don't want to limit it to a specific input. So
Okay,
when
ma'am.
I am comparing to okay, whenever you're comparing two things, you should compare it for the general case scenario, right? Not for a specific case scenario. And for
Right.
this general case scenario, we will have like for most of the inputs from C to infinity, we will be that will be a larger size of the inputs, right? So this is just limited from n equals to 1 to C. Just for C values, A3 will be the fastest or something. Okay, but
Right, ma'am.
after that from some like 100,000 or millions of values, my A3 will have a like worse running time as compared to A1.
Okay, ma'am. Okay.
So when we are comparing for the general scenario, like whenever we are performing this asymptotic complexity analysis, or we are comparing these two algorithms, we compare it for the general case scenario. Okay, so here we have my f of n, like for larger values of n, we have my f of n is be bounded, upper bounded by h of n. My function f of n will never take a value that is greater than h of n. Okay, does this make sense? Is this clear?
Yes, ma'am.
Yes, ma'am.
Yes.
Yeah. Okay. So now the reverse thing. Suppose we are saying that my f of n will not take a value greater than h of n, but h of n will always take a value at least f of n, right? So is there a way to represent that? So can we say that my function will always be greater than equal to something else? Just the opposite of that, exact opposite of that.
What
And
omega?
that is the omega notation. So h of n will always be omega of f of n. Okay, this is just a notation, but throughout this course, we will only be looking into order notation. Okay, this omega notation will be you will be seeing omega notation very rarely in this course. Okay, this is just for information and knowing what this idea is. Okay. Now comes to the theta notation. So now see, like for this scenario for A1 and A2, if we are going to compare A1 and A2, what will happen when you compare A1 and A2? Like for some value, I agree, for n is equal to 1, n is equal to 2, n is equal to 3, my A1 will be less than A2. The f of n will be less than g of n. I agree for that. But when you go to infinite values, like 100,000 values, or like values like 100,000 or 20,000 or a million, n equals to a million or something like that, when n tends to infinity, what happens to these two functions? Okay, so what happens is these two functions will tend to become almost equal. Okay, what the values will not have much difference between them. So when my functions when my value of n keeps on increasing, the trend along which the value of the function will also increase will almost be similar to both of them. Okay, so that is why we say that f of n will be g equals to g of n. For a like not exactly, the value may not be exactly equal, but it will be very close to each other. Okay, and at that point, like when we are comparing 1 million, suppose the value of f of n is like 1 million 2 and value of g of n is 1 million 3, then it doesn't really make a difference at that point of time. Okay, so what we say is f of n and g of n will have the same asymptotic complexity. Okay, and this is denoted using the theta notation. So we will say that f of n is equal to theta of g of n. And hence what will happen? G of n will also be equal to theta of f of n. Any confusions or any doubts till now, or this is clear?
No, ma'am, clear.
Ma'am,
Yes.
can you please explain it once again?
Which part?
The theta concept.
Okay, so the theta notation, right? Suppose, okay, I'll just erase this one. So the question is, what happens to A1 and A2? What we are discussing is what happens to A1 and A2. Okay, so but like how related are this A1 and A2? So what happens is, suppose n is equal to 1. Which one will be better between A1 and A2? A1, right? Hello?
Yes.
Yeah, suppose n is equal to 1, then A1 is better, right? Now suppose n is equal to 2, which one will be better? Again, we can see that A1 will be better. Okay, but when n is equal to 100, what will happen? Okay, so what will happen is we will be having 100 square times 2, which will be 100 into 2 plus 304. Okay, so something like 20,304. And this will give you 30,000 305. Okay? Hello?
Yes, ma'am.
Yeah, so still A1 is better than A2. Okay? Now suppose we go to n equals to 10,000. What will be the values? Just use this one.
Nearly getting same.
Sorry?
Getting same. Nearly same.
What are the values? Can you please share? Did you calculate? Uh, 1, 2, 3, 4, 5, 6, 7, 8, 2, 1, 2, 3, 4. Here I will be having a 3 and this will be 4. And here we will have 3, 1, 2, 3, 4, 3, 0, 0, 5. Okay?
No, 3 will be
Yes, ma'am.
What will be the
3
value?
will be before.
Sorry?
3 will in fifth position. In the first case, 3 will be in fifth position. Yeah.
Okay. And in the second case also, in both the cases would be the same, right?
Yes, ma'am.
Okay,
Yes, ma'am.
something like this will come up, okay? And then when you keep on increasing n, okay, what will happen? These values will be different. These values will still be different. A1 will still have a value less than A2. Hello? Someone is saying something, I guess, or the mic is on. Okay, anyways, so when we keep on increasing the value of n, these values will still be different. A1 will still be less than A2, but the difference wouldn't make such a difference. Like this, whatever this difference in the values will be there, it wouldn't be so much to matter too much. It wouldn't be so much that it will matter. Okay, that's what I'm trying to say. So what I'm trying to say is, in the long run, both of these functions will grow almost similar to each other. So this function will grow on a quadratic scale. This function will also grow on a quadratic scale. So this is A1 and this will be A2. And slowly the difference wouldn't be that much to notice about. Okay, that's what I'm trying to say. That although the functions, this function will have a value less than this function, but the growth of these functions will be very similar to each other, and the difference among these exact values wouldn't matter too much. Is this statement making sense?
Yes,
Yes,
ma'am.
ma'am.
Okay, so what we are saying is, what we use is, we will use the theta notation, which will denote this equivalence. Okay, so we say that f of n is equal to theta of g of n, which will denote that my f of n and g of n functions grow equally to each other. So in the manner that g of n grows, whether it's quadratic or linear or like you on a cubic or whatever it is, okay? On the manner in which g of n grows, f of n also grows in the exact same manner. This is what we are trying to say using this. So if this is the showing the equivalence between these two functions, the growth of these two functions are equivalent. The way these two functions grow are equal to each other. Okay,
Yes.
so suppose if my f of n grows as equally with g of n, then g of n should also grow equally like f of n, right?
Yeah.
Right? So if my f of n is equal to theta of g of n, then my g of n will also be equal to theta of f of n. Are these two statements clear?
Yes.
Yes, ma'am.
Okay. So yeah. So this is the theta notation. So now notice that if my f of n is growing equal to g of n, then can I say this statement? that f of n is also equal to order of g of n? If f of n and g of n are growing equally, okay, then my g of n will always be greater than equal to f of n. Agreed or not?
Yes.
Yes, ma'am.
Similarly,
I'm not getting.
the growth of, okay, which part did you not get?
The equal to order is equal to.
I'm sorry?
Order is equal to.
Hello?
F of
Order.
n is equal to order of g of n. I think. Yeah.
Okay. Yeah, okay, okay, wait. Give me a minute. All right. So f of n is equal to theta of g of n, right? So I can say that suppose g of n is quadratic, then f of n is also quadratic,
Yes.
right? Now, what does this statement mean? F of n is equal to order of h of n. It means that when n tends to infinity, my f of n will never have a value greater than h of n. When n
Mm-hmm.
tends to infinity, f of n will always be less than
Uh,
equal to h of n,
h of
right?
n. Yes. Less than or equal to. Yes.
Right? So if my f of n and g of n are growing equally, if my f of n and g of n are growing equally,
Equal.
will we have, will we ever have a scenario that, like, can
H
we
of n.
claim that f of n will always be less than equal to g of n, some constant times g of n? When n tends to
Yes.
infinity, can we claim that my f of n will always be less than equals to some constant times g of
We have to do conditional concept.
Yes, ma'am.
n? Right? So this means what? This means my f of n is also equal to order of g of n. Do you agree to this?
Yes, ma'am.
Yes.
But ma'am, can
Yes.
we say the vice versa? We cannot say, right, g of n is equal to order of f of n as we have calculated the exact values. Or
No,
just
we
by
have
looking at the power,
see,
we can say that a converse is also true.
exactly. We can look into the power and say the converse is also true, right? Because we
Okay.
can just multiply with some constant. Just multiply with some constant and you will get
Okay.
something like this, right? When n tends to infinity, g of n will always be less than equals to some constant times f of n. Let's say 4 times f of n. Is it true or not?
Yes.
Constant
It's
time we
maybe.
can
It's
say.
maybe.
Yes.
Yeah. But
Right?
how about if we if you want to say like g of n is equal to order of f of n, can we say that?
Yeah, we can
We
say that
can.
because in asymptotic complexity, we do not care about the constants.
Okay. Okay.
Okay, why I will come to that. I'll come to why. Okay. So we can say that g of n will also be equals to order of f of n. So this part I should have come a little bit later. So what happens is in asymptotic complexity, we do not care too much about the constants and the lower order values. Okay, so here, for example, in this, let's go back little bit. Okay, we have this f of n is equal to theta of g of n, right? We have f of n is equal to theta of g of n. We are agreeing to this, right? All of us are agreeing to
Yes,
this,
ma'am.
right?
Yes.
Yeah. So now what it means is my f of n will be growing equally just like g of n. Whatever I have the function, if my g of n is quadratic, my f of n is quadratic. If g of n is cubic, my f of n is cubic. So however my g of n is growing, my f of n is also growing very similar to each other. Right? Now, suppose I say f of n times 10 and g of n times 1000. Now what will happen? they will still be quadratic, right? They will
Yes.
growing in the same way as before. My g of n was earlier
Yes,
quadratic.
they are.
So yeah, now also g of n will be quadratic, f of n will also be quadratic. This
Quadratic.
entire function will be quadratic and this entire function will also be quadratic. So the way they were growing, it will still grow that way. Okay. After some point of time, like earlier, let's say for some particular example, for some particular values of f of n and g of n, after n is equal to 10,000, the difference was very less. Okay. Now it may be the case that n becomes 100,000 or 500,000 or something like that. This value may get increased. But when we are going towards infinity, when n tends towards infinity, it will still grow in the same way and the difference wouldn't matter too much. Okay, so even if we have this 10 times f of n or 100,000 times g of n, whatever it may be, even though the running time of the function, the exact time taken to run the function will slightly differ, we can say the growth rate of the functions will be same to each other and it will be theta. And hence we use the theta notation. What I mean by growth rate is the rate of growing, how the function is growing, like whether it is a quadratically growing or is it growing cubically, how the function is growing. That will not change. Okay, with change in the values of constants. Okay, similarly, if we add some lower order terms also, if I say that f of n is now changed to f of n plus some 500n. Okay, and g of n is now changed to g of n plus 1000 n square. If my g of n was cubic, okay, and f of n was also cubic, somebody's speakers on and I'm hearing some motorbikes and stuff. So can you please mute? Okay. Yeah. So if my f of n is cubic and g of n is cubic, and I'm going to add these two terms now, then what will happen? It will still be, both of them will still be cubic. Okay. So the rate at which these functions will grow, that will still be cubic. And hence it will still be theta of, like it will still be, we can still use the theta notation. Is this making sense? Is this clear?
Yes.
Okay, any doubts till now?
Ma'am, so the rate will be depend on the power of it.
Exactly. The highest power of the function.
Okay.
Okay. But yeah, hello?
Yeah, ma'am.
Yes. So now does this statement make sense? So now we will just back up a little bit and discuss this part. So we have f of n is equal to theta of g of n. So can we say that f of n is equal to order of g of n and g of n is equal to order of f of n? Are these
Yes,
two
ma'am.
statements true? Right?
Yes, ma'am.
Yeah. So now if we are having f of n is equal to theta of g of n, then my f of n will also be equal to order of g of n and g of n will also be equal to order of f.
Ma'am, is this because they never intersect? Is this, are we equating this because they will never intersect, or
Yeah, in a way you can say that. Yes.
okay, ma'am.
That is like that is not the exact terms that we use, that they never intersect, but yes, that holds true.
Okay, ma'am. Okay.
Any other doubts?
No, ma'am.
Okay, so in during the course, like during this course, you will find some really complicated functions also that involves logarithm functions and exponential functions also. should look into how the function grows rather than the values of the function for some specific numbers. Okay, so you should look how the function grows, like logarithm grows like this and quadratic function grows like this, right? So if I say that one of your functions f of n is quadratic, suppose n squared, and g of n is logarithmic, like log of n, then what will be the relationship between the two? If we are asked for that, then instead of like substituting for n is equal to 1 or n is equal to 2 or stuff like that, you should look into exactly how the function behaves for larger values of n and how the function grows when n keeps on increasing rather than for some specific values of n. Okay, to denote them using order and order notations. Okay, we will be looking mostly into order notations only, and very rarely we will be looking into theta or omega notations. Okay, I hope this part is clear. If you have any doubts,
Ma'am,
yes.
ma'am, could you please explain for logarithmic function again?
No, what I was just saying is, if you are having, this is just an example. Suppose you are given two functions, then rather than substituting some simple values for n and finding which of these function is having a lower value and which is having a greater value, what you should do is you should look into how the function grows over increasing while you increase the value of n. When you keep increasing the value of n, what happens? Does the functions like how do the functions behave when your n keeps on increasing? That is something that you should look into, and that is something yeah, so that is something that you should look into rather than substituting some particular values and seeing whether one function is behaving better than the other. Like for example, if we are having logarithm of n and n squared, this was just an example. If my f of n is n squared and g of n is log n, for n is equal to 1, my g of n becomes 0 and f of n is equal to 1, right? So g of n is less than f of n. If you just keep substituting one of these values, I substituted n equals to 1, and I will say that g of n is equal to order of f of n. This is wrong, okay? In reality, when n keeps on increasing, my f of n tends to have larger values for n as compared to g of n. Okay, so f of n will have larger values as compared to g of n when n keeps on increasing. So that is why the fact is f of n is in fact order of g of n. Okay, so this was just an example to explain that when you are asked to compare between any two functions, rather than just substituting one or two values, I would suggest you to look into how the function grows over increasing the value with n. Like when you keep on increasing n, what happens to this function? You should look into that. Okay.
Ma'am, it should be g of n
Yeah.
equal to order of f of n.
Yes, ma'am.
Yes.
Yes, ma'am. G of n is the order
Oh,
of
yeah,
f of
yeah,
n.
yeah, 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 yeah. Sorry. I was just confused. Okay, yes, you are right. Uh, for this scenario, what happens?
G of n is order of f of n, ma'am, because in for log n, the maximum value will be for n square.
Yes, yeah. No, I was just trying an example when I will have um, g of n will be greater than f of n for some particular value. Like maybe, okay, so what I was trying to say is, okay, this is true. So for some particular value of n, if you are having a function where one of the function is behaving greater than the other function, then that does not mean that that function is a greater function. That is what all I was trying to explain. Okay.
Okay, ma'am.
Any doubts?
Mhm.
Yes.
No, ma'am.
No, ma'am.
So, uh,
Ma'am, some background voice coming.
Somebody was saying something.
Sorry.
Background noise from my side or something? Hello?
No, ma'am,
Ma'am,
not from
it's
your
okay.
side.
There is no background noise from your side.
Okay, somebody was asking, does anybody has any doubt or should I go to the next part?
Ma'am, can I ask doubt?
Yes.
Ma'am, in case of tight bounds, it was given in the slides like C of g of x is less than or equal to f of x, and then f of x is less than or equal to c to g of x.
Oh, this one. Are you talking about this one?
It was given in the slides.
Are you talking about these figures in the slides?
Yeah, yes, ma'am. For the tight bounds,
Yes.
theta.
Yeah. So this one, I should we have discussed this one, right? This order of geometry.
Yes, ma'am.
So omega of geometry will also be the similar because it's just the opposite of this, right? This is also clear, right?
Yes, ma'am.
Yeah, I was coming to this one. Okay. So now when we have discussed that f of n and g of n are growing equivalently, right? For theta of g of n, right? What happens if my g of n is quadratic? Then my f of n will also be quadratic. That's what we had discussed, right? So my f of n and g of n are growing equivalently. So we can say that we had discussed this earlier. So we can say that f of n is less than equal to some c times g of n. That is why we had that f of n is equal to order of g of n. Do you agree to that? We
Yes,
had
ma'am.
discussed this earlier, right?
Yes, ma'am.
Yeah.
Yes, ma'am.
Similarly, we also had that g of n is less than equal to some c times f of n. So that is some, let's say this is c1 and this is c2, right? And that's why my f of g of n was equal to order of f of n. Remember this too? So
Yes, ma'am.
now when we can look into carefully into these two equations, what will happen? My f of n is less than equal to some constant c1 times g of n, but is also greater than equal to some constant 1 by c2 times g of n. Right? This is just basically
Yes.
I'm combining these two equations here. Okay, so what happens is when my two functions are growing equivalently, two quadratic functions, two cubic functions, suppose two of these functions are growing together, okay, they are growing equivalently, the growth rate of these functions are same, then what happens? This condition holds true. For some constant C1, let's say uh, I'm going to use D1. Okay, for some constant D1, D1 of G of n will be less than equals to f of n times f of n, which will be less than equals to D2 times G of n. Okay, is this clear?
Yes, ma'am.
This is exactly what this function means. So in other ways, we can interpret that in a different way also we can interpret. Suppose if my function f of n satisfies this condition. Suppose if we have the condition that my f of n is greater than equal to some constant times g of n and f of n is less than equals to some constant times g of n, then this will imply that f of n is equal to theta of g of n. Okay. Similarly, if we
Yes, ma'am.
see, if we can reverse this a little bit, we will have my g of n will be less than equals to 1 by d1 times f of n and some constant 1 by d2 times f of n, which will
Yes, ma'am.
again imply that g of n is equal to theta of f of n. Okay, so whether you see like two functions are growing equivalently, and that's why we say that this the functions are asymptotically equal. Okay, so f of n is equal to theta of g of n, then this condition will definitely be satisfied. On the other hand, if such a condition gets satisfied, if such a condition holds true, then it will definitely be the scenario that f of n is equal to theta of g of n. Okay. So saying f of n is equal to theta of g of n is equivalent to saying this condition, and saying this condition is also equivalent to saying this asymptotic notation, using this asymptotic notation. Is this clear?
Yes, ma'am.
Okay. So now we will see what's next.
Ma'am,
Yes.
so here we can say if f of n is equal to theta of g of n, then f of n is must be order of g of n. Is it true?
I'm sorry, can you please repeat? There was some break in your voice.
If f of n is equals to theta of g of n,
Okay, if
then
f of n is equal to theta of g of n,
we can also say that f of n is order of g of n.
yes, that is what we have already discussed. Yes, this holds true. It's not just that f of n is equal to order of g of n, g
It's
of n
always
will also be equal to order of f of n.
this will be always true with first
This
conditions.
will both of the conditions will always be true.
Okay.
So from these conditions, you can also imply this, right? F of n, sorry, g of n is the omega
Theta is
of f of n, and f of n will be omega of g of n. So if f of n is equal to theta of g of n, then all of these four conditions will hold true.
okay.
Okay?
Yes.
Any other doubts? Any doubts?
No, ma'am.
Okay. So then we'll go to the next part. These are just examples of how to calculate the complexity. So calculating for, if suppose we just have to compute a plus b, then this will be having order of one. No matter what we will giving the values, always we will assume that the addition operation is taking unit amount of time, and it doesn't depend on the exact whatever input size we are giving. Okay, whatever the number may be, we will just be performing one addition operation. So my time will always be proportional to this single addition operation, and hence my time complexity is order of one. Okay. Similarly, for single loop, if I have just one loop, I'm just going to go through for every particular value. So my order in the order notation, we will be having the time complexity will be order of n. Okay. So you can just look into different examples here, and if you have any doubts, then you can get back to this. So these are different examples. Okay. So now,
Ma'am, I have a doubt
yes,
regarding this
example.
calculating complexity in the examples. In the
Okay.
lecture, there was a part where sir was explaining that uh, for a problem like finding the binary, finding the number of bits of a
Yeah.
given input, right?
Okay.
uh, that takes time, proportional to log n. But sir
Yes.
also said that the time is linear. I didn't understand that, understood that thing. I mean, if the order is of log n, then how can it be linear?
No, if it is log n, then it is not linear. It is logarithmic.
No, actually, sir also said this in the lecture that something like this. The time is proportional to log. Can you explain that part from the lecture?
Can you please tag like post this on discourse and like tag the exact like
Okay, ma'am. Okay.
point of the lecture or something. So I can look into the lecture. I haven't yet looked into the lectures videos. That's why I'm not really aware of what
Okay,
you
ma'am.
are
Okay, understood.
saying right now.
Yeah, ma'am. I'll post after this class.
Yeah, sure. Or maybe you can just text me, or anyway, you can just communicate with me later because I haven't looked into the lectures as of now. Okay.
Okay, ma'am.
Yeah, sure. So, any other doubts?
Ma'am, can you explain the example of nested loops for complexity ones?
Sorry?
Can you explain the nested loop for complexity?
Next step.
Nested loops.
Okay, nested loops. Yeah, sure. Okay, we'll start from here. What happens here? Uh, just let's just take an example. N is equal to 5. So I'm just looking into this particular example. Okay. So my what it does is for I is equal to one range n, for j is equal to range n, it's just adding s equals to s plus 1. Okay. So how many times this will be executed? That is what this loop will get executed. That is what we are trying to compute. Okay. So now for I is equal to 0, how many times this inner loop will run?
5 times.
5 times.
It
For
will
I is equal to 1, how many times it will run?
5.
Uh,
Ma'am,
sorry?
total 25 times run.
Exactly. It will run for 25 times. Now, suppose you don't know the value of n. Okay. Suppose we don't know the value of n. What will we do now? I don't know this thing. So what will be the time? How many times the inner loop will run for I is equal to 0?
N times.
N times. How many times the inner loop will run for I is equal to 1?
10
N
times.
times.
Okay, so my I goes from from what? 0 to n minus 1, right?
Yes.
And every single time it will run n times. Do you agree to this?
Yes,
Yes,
ma'am.
Ma'am,
ma'am.
actually it
Yes.
should run for n plus 1 times, not n times.
Why n
Because
plus
it
1
will
times?
check, because it will check and then the loop will finish, right?
No, see, for j in range
For
n, what
I,
will happen?
but that's what I'm saying. It will, for let's say for 5, right? It will run
Okay.
for 5 times, and for the sixth time it will check and it won't go inside. So it will check actually for the 6 times.
Yeah,
And
yeah,
it will
I agree.
execute for 5 times. So it will be n plus 1. It
Yeah,
should be n plus
asking
1.
the, I'm not asking the number of comparisons. I'm asking the number of times the loop body is
Okay,
executed.
body is executing. Okay, then. Then n times.
Right? So how for I is equal I goes from 0 to n minus 1, which is n times, and for each of the time it is running, the inner loop is running for n times, right? Hello.
Yes, ma'am.
Yes, ma'am. Correct.
So the total number of times this extreme inner loop, this part, is running for a total of order of n squared times. Let's forget about the order notation. So this part of the code will run for a total of n squared times. Do you agree to that?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
So this operation will be performed n squared times, right? So that is
Yes.
why
Yes.
we are saying, yeah, that's why. So the complexity of this entire code will be for this particular statement, this equal operation will be performed order of 1 time. This comparison will be performed order of n plus 1 time, just like ma'am just now pointed out. This comparison will be performed order of n plus 1 time, and this operation will be performed order of n squared times. Right? Let's
Yes, ma'am.
forget about this
Yes.
order. Right? So now the algorithm, the time taken for this algorithm to run will be f of n will be equals to 1 plus n plus 1 plus n plus 1 plus n square, right? So in
Yes,
the
ma'am.
order notation, we do not care about the constant factors. We do not care about the lower orders. We only take the highest order, whatever is the highest order. So n squared is the highest order and hence f of n will be order of n squared. Is this clear?
Yes.
Yes, ma'am.
Yes.
Yes, ma'am.
Okay. So after this, we'll go to the three nested loops also. It is the exact same procedure. So I would suggest you to just try it out once. If you are not finding this order of n cube, if you are stuck somewhere, then please ping me. I'll clear it again. So
Ma'am, can you please scroll up?
yeah, sure.
I want to see what you have, what you wrote, that part I want to see. And you said the first one is 1, order of 1, then where you wrote, yeah. Then it should
Ma'am,
be n plus, ma'am, it should be multiply, right? N plus 1 into n. It should be like that, right?
Yeah. This will be n plus 1 times n plus 1. Sorry. Okay. So this
excuse
will
me, ma'am.
become
No, I think it should be 1 plus n plus 1 into n plus 1
1 plus
plus
n plus 1.
1 plus
Okay. Plus
n into n plus 1.
N into n plus 1. Yes.
Yeah.
okay. Plus
Then n square.
n square. Right? Yeah.
But why
Yeah.
that n into n plus 1? I didn't get that.
For this particular comparison, there is a comparison operation that's happening here, right? So now
Yes,
for
yes.
every value of I, we will be comparing n plus 1 times.
Okay, okay.
That's one. Okay. Yeah, you are right. This is a So this will actually become order of n squared. Okay. Hello?
Ma'am, can you
Yes.
please explain the binary search?
Yeah, I'll come to that. I'll come to that after this. Any
Okay.
doubts till now? Then otherwise we'll just go to the next part. The searching and sorting algorithms.
No doubt,
No,
ma'am.
ma'am, no doubt.
Okay. So for the searching algorithm, searching is basically we are having the problem is we are given n numbers and we want to search for the location of a number. Okay, we want to see if a number is present in that list of numbers, where it is present, and if it is not present, then you have to say that. Okay, just 1 second. Before that, the recursive solution is this there in the slides and in the videos?
Yes, ma'am, it is.
Okay, so we should discuss this part. This part is a little bit tricky. So what happens here is we need to compute the time of this algorithm, right? So now this algorithm, let's say my algorithm is taking some f of n time. Okay, so now I want to calculate how much time, what is this function? I want to compute this f of n function. Okay, so now this comparison operation will be performed one time, and this operation can be performed in one time, although this is an if condition, but if this if is executed, then this will take order of one time. Okay.
Okay, ma'am.
Okay, can you please, whoever has unmuted, can you please mute? I'm hearing ads now. Okay, but now what happens is, suppose if the if condition is not satisfied, then this statement will be executed. Okay, so what will be the time taken to execute this particular statement? Okay, so now this operation will take unit amount of time, this particular multiplication operation. And now this is what? This is factorial of n minus 1, which means that whatever will be the time taken to run this particular algorithm on an input of size n minus 1. Right? So now this will be equal to f of n minus 1. Do you agree to this?
Yes, ma'am.
So the total running time of this particular algorithm will be f of n is equal to f of n minus 1 time 1 plus order of 1. This is what is called a recurrence relation or a recursive statement. Okay, it just recurses on a different value. Okay, so this is on a lower value. Okay, so this is called a recurrence relation or a recursive statement. Okay, so now what happens is, if you keep on solving this, if I just substitute this value, f of n minus 1 will be what now? F of n minus 2 plus order of 1 whole plus order of 1, right? And this will keep on happening. So I will be having this order of 1 will occur n times. If I keep on doing this, my order of 1 will come n times, right? So this will be n
Yes.
times order of 1, which is basically equal to order of n. Is this clear or any doubts?
No, ma'am, this is clear.
Okay, so then we will go to the next part, which is searching algorithm. So searching algorithm is basically, the question here is, we are given a list of numbers, we are given a list of n numbers, and what we want to do is, we will be giving, I'll give you one more number, let's say some number b. I give you a number v, and I want you to find the position where v is present in this particular list of numbers. Okay, so you are having a bunch of books. I want you to find the book in that bunch of books, or this is that's an example. Okay, so similarly, there are a bunch of values, and I want you to find that value in this bunch of numbers. Okay, so that is what the question is. So what exactly is a very trivial algorithm to do this? How do you solve this problem? A very simple solution would be, I pick this first number, check if it is equal to b. Is this number equal to b? If it is equal, then I just return this particular position. I say, hey, the number v is present in the first position. No, let's go to the second number. If the second number is the second number equal to b, I just compare between them. Okay, if this number is actually equal to b, then I say that, okay, this number is equal to b, and hence b is present in the second position. But if it is not equal to b, then I go to the third position. And I keep on checking this, I keep on doing this until I find the position of b in that list. Suppose I have exhausted all the numbers, I searched for all of these numbers, and I realized v is not present in any of these numbers, then I can just say that my v is not present in this list of numbers. Okay, so this is what is called as linear search. This is the algorithm for linear search. What it does is, it's just given a list of numbers, one to first position, second position, third position, and so on. We are having this list of numbers. It just starts from the first point till the last number and just keeps on checking with b. If this number is equal to b, then it just returns that position. Otherwise, it just keeps on checking until the last number. Once it exhausts all of these numbers, it's just returning false. Okay, so if you, this is the algorithm for that. For I is equal to 1 to the last number, which is I equals to 0 to the n minus 1th position. Okay, whatever is the length of the minus 1, that is the position, length of v minus 1 at position, the n minus 1 at position. It just keeps on checking, comparing v with L of I. If it is equal, then it returns I, which is the position of the of the number v in the list. Otherwise, it will just return false. Okay. So this is also assuming that no numbers are repeated, and if there are repeated numbers, then we are just returning the first instance. Okay. So this is what linear search is. But now suppose I say that, hey, you don't have to do all of this. I have already sorted the numbers. I have sorted all of the numbers. So now my numbers are sorted in increasing order. So I have the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, and so on. Okay, this is just a crude example. Okay, so now suppose I'm telling you, hey, I have already sorted the numbers, and now you go ahead and find the position of 9 in this list of numbers. Let's say 6 is not here. Okay, yeah. So now what do we do? Obviously, we can go via the crude implementation, the normal implementation, wherein we just start from the first number and we keep on checking if it is 9, and we can find that my ninth number is present in the 8th position, and I can tell you that hey, 9 is present in the 8th position. But other than that, I can also do something intelligent and smart here. Instead of going to the ninth position, I'll just start from the middle one. I'll start from middle number, and I see that this is my middle number, which is 5, and my 5 is not equal to 9, but 5 is indeed less than 9. And I already know that my numbers are sorted in increasing order, so my 9 cannot occur within this part of the list. Right? So obviously every number here is less than 5, which means every one of these numbers will be less than 9. So my 9 cannot occur anywhere in this half. So I just cut out this part. I'll just look into the remaining part of the list. And suppose I'm already telling you that none of the numbers are repeated, okay? So that means what? Because 5 is strictly less than 9, that means my 9 will be somewhere within this region only. I can also cut off 5 here. I can just start from 7 and search between 10. From 7 to 10. I can just search between this list of numbers. Right? So now what happens again in this list of numbers, I can perform linear search here again. I can just scan one by one and find where my 9 is, or I can just skip that and I'll just go to the middle number. Now there are two middle numbers, 8 and 9. So what I'll do is I'll just choose 8, just the floor number or floor or something. Okay, the lower number. So I'll just go to the lower middle number, which is 8, and I'll see if 8 is equal to 9. Okay, is this true? No. Rather, I know that my 8 is less than 9. So which again means that my 9 cannot be anywhere before 8. Right? So my 9 has to be there somewhere between these two numbers. So I will only search in these last two numbers and try to find 9. So among these two numbers, I want the middle number, but there are only two numbers, and I'm just using the notation that I'll go with the lower middle number using the floor notation. So I'm just going to the lower index of among these two numbers, which is this index, and I am finding that there is 9 existing in this particular position. So I return this particular index. Is this algorithm clear?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Okay. Right. So this particular algorithm is called as binary search algorithm. Okay. So before that, I actually forgot to analyze the time complexity of linear search. Here it is very simple. We just scan from 1 to the last number, which is basically, so it will run like n times. It will compare under the worst case scenario. For the worst case scenario, what will happen? My n is not present, so it will run for the entire list. Okay, entire list of n numbers. So that is why for my linear search, the worst case running time is order of n, right? Similarly, my best case running time will be when my n is just present in the first number. I'll just do one comparison and I'll find that my n is present at the first index, so I'll just return there itself. So the order will be order of 1. So the best case time will be order of 1, but the worst case time will be order of n. But what about the average case? In general, what will happen? It can lie somewhere around here, right? Or around here, in between. Okay. So it will be something in order of n only, because we will have to scan about at least about like n minus 2 numbers or n minus 3 numbers or n minus 4 numbers or something like that. So you can imagine n to be like 100,000 or something. And when my n is lying something somewhere in between, then we will be having to run for like n minus 5 numbers or n minus 6 numbers or n minus 10 numbers. And it will not matter too much, right? So we will have a average case will also be order of n. Okay.
Ma'am,
Now, yes.
here also don't we need to look at the number of comparisons for the for loop, like in the
We can
previous.
look into the number of comparisons. Here it is order. How many comparisons here? It will be n plus 1 comparisons. This will run a total of n times. This will run at most 1 time, right? And this will run at most 1 time, right? This is less than equal to 1. This is less than equal to 1. You agree? Now notice that if this is running, then this is not running. Okay. So what will be my f of n here? So f of n will be n plus 1 comparisons for the for loop. Now the for loop is actually running n times. Okay. This thing will be running n times. And this one will be executed, or this one will be executed exactly once. So 1. So this is actually, you can just ignore the constant. This will be 2n plus 2. So you can ignore the constants and the lower order terms and you will get order of n. This is obviously like the average case scenario where I'm taking like I'm just comparing between these two. If you want the worst case, the worst case will be this will not be executed at all and this will get executed. Okay. Any doubts?
No,
Is this
ma'am.
clear how this is this clear how you got this order of n for the worst case?
Yes,
Yes,
ma'am.
ma'am. Clear.
Yeah, so what happens is when your for loop, even though your for loop is running for the number of comparisons is n plus 1, because in the order notation we are just ignoring the lower order terms, so it will just become order of n. So we don't really need to check exactly how many comparisons are being made. Okay, you can just see that this is running for n times, so you can just say that okay, this is order of n. Okay, you don't have to like exactly calculate how many exactly how many times the comparison has been performed, how many times this operation has been performed, and all of that. Okay? You can just take like look into it and see that okay, this is running for some n times, then it will be order of n. Even if the number of comparisons is becoming n plus 1 or n plus 2 or n plus 3, it doesn't really matter as long as it is not n times. Okay, you can just look into the okay, this is n, this is like this, the number of comparisons will be maybe slightly 1 or 2 times more than that, but it will be fine. Okay, this is just a trick on how to know the complexity. Okay, so now coming to the running time complexity for binary search. So for binary search, what will be the running time complexity? That we need to analyze now. So what happens is for binary search, this is the algorithm. Okay, this is the iterative algorithm. And here we don't have a for loop, so we don't really know exactly how many times our algorithm will be running. Okay. This is the recursive implementation. This is the iterative implementation. You can look into this implementation. Okay. And now Yeah, the analysis. Okay. So what will be the analysis? So what happens here? What doing here? I am going to the center value. So let's say the binary search takes order of f of n. Okay, the time taken for to perform this binary search is some order of f of n. And now I will be calculating the worst case. We will come to the best case after this. Okay. So in the worst case, what will happen? What I'll do? The worst case is when the number is not present in the list. Okay, so you'll have to just look through all of these without any result. So for binary search, I just invoke this function and I go to the middle value and I see if the middle value and I perform this particular operation. Right, I do this check which will actually take order. This will perform one time. This operation will be performed exactly once. Then we will perform exactly once this particular condition checking, and we will not be returning this value for the first iteration. For the first time when I will invoke this, I will neither be returning false nor I will be returning mid. Okay, because my this is, I'm assuming this is the worst case, and that's why my number is not there. So it will not be false. The high value is the last number. Low value is the first index, high value is the last index, which means that the first index, last index minus the first index is greater than equal to 0. Okay, it will not be less than 0 because the list is not empty. So now this will not be true, this will not be true, and hence all of these comparisons will be performed exactly once, but the return operations will not be executed. So now again, this operation will be uh, executed, which means this will be run exactly once, right? Now, what will happen? Either I will perform this one or I will perform this one. Okay, so now what is this? This is basically I am performing a binary search on one particular half of the list, right? So I had this initial 10 numbers 1, 2, 3, 4, 5, 7, 8, 9, and 10. I had these 10 numbers in this list. I started from 5, and now what I'm doing is I'm just discarding one half of the list and I'm just considering only the other half. So either I will consider this half if I'm searching for 9, but if I'm searching for 3, I will be discarding this half and I will be looking into this half. Either way, I will just look into one of the halves of this list. I will not be looking into the entire list the second time. I'll just look into either one of these halves, right? So now my list half, the size of my list has now reduced by half in the second iteration, the second recursion. The second time I will be calling this binary search function, my list size will now be half. Okay, and what will be the total time? This will be f of n plus this will be 4 plus 4. So this 4, we can say this is equal to some order of 1. Okay, and this part is order. Okay, and there will be f of n by 2. So the standard notation for using this, instead of writing f of n, standard notation is to use t of n. T basically represents time. Okay, so capital T represents time. So T of n will be the time taken on this n length input will be equal to the time taken on the n by 2 length input plus some order of 1. Do you agree to this statement? Is this
Yes, ma'am.
statement clear or any doubts is there?
No, ma'am, it's clear.
Okay, so now when you keep on, when you solve this equation, this is a recursion equation. When you solve this equation, so what will happen? I have T of n equals to T of n by 2 plus order of 1. This will be equal to T of n by 4 plus order of 1 plus order of 1.
Yes.
Right? Now this will be equal to T of n by 2 cube. This is 2 squared. And then I am dividing again by 2. So this becomes 2 cube. Okay. Plus order of 1 plus order of 1 plus order of 1. Right? And this will go on. And when you solve this, you will realize that this will become mm, logarithm of n times order of 1. How this will come? It's basically T of 1 plus log of n times order of 1. This will come to something like this. And this will be equal to T of 1 is actually equal to 1 because it basically means that we have one number in this entire list, right? So my n is equal to 1. When n is equal to 1, what will happen? This is my, this is actually my, what is it? This is the worst case scenario. So my T of 1 will be basically this high minus low will be either will it be less than 0 or this will hold true and I'll just go to T of 0 and I will have something of this form. Okay, I get something like T of n times log n minus 1 or something. I don't exactly remember the exact value, but if you solve this, you will get something like T of log n minus 1 or something. Okay,
Okay, ma'am.
it will be log n. It will be log n. Log n times log n. So when you, so my T of 1 will basically, it means that I'm having exactly one number. So I'm just comparing that for one particular number and we will have T of 1 will be equal to order of 1, which will actually become, this thing will be something, this is some order of log n times order of 1 and this will actually become order of log. This is the scenario when we have the worst case time complexity. Okay.
Yes, ma'am.
Now what is the best case? In linear
Same as the worst.
no, why?
Order of
In
1.
order of 1. The best case will occur when my number, the number that I'm searching for is exactly the middle number. So what I do is I will be looking, so I have 1, 2, 3, 4, 5, 7, 8, 9 and 10, right? This was my list. And what was I doing? I was starting from 5. Now, suppose I was initially searching for 5 itself. Then what will happen? I'll just go to 5 and I'll compare this 5 with my B. And I'll see that, okay, these two are same and I'll just return this middle value and I'll exit there itself. So it will be order of 1. My best case scenario for this case will occur when my number, the number I am searching for is in the middle, is the middle number, or it is present in the middle index. Okay, so that is my best case scenario. For linear case, for the linear search case, my best case scenario was when the number was the first element of the list. But here, the best case occurs when the element is present in the middle index of the middlemost index of the list. Okay, but nevertheless, the best case running time will be order of 1. Okay, is this clear or do you have any other doubts?
No, ma'am, it's clear.
Okay.
Clear, ma'am.
Sorry, just a minute. Something. Hello, am I still connected?
Yes, ma'am.
Just give me 1 minute. Some. Okay. So now coming to the sorting algorithm. So now what happens is I had already told you, like we have already put the we are okay. So what this sorting algorithm is, so the problem here is we are given a list of numbers. Let's say 9, 3, 2, 1, 6, 4, 8, 10, 5, 7. I've given this list of numbers, and what I want is I want to sort them in increasing order. So my output should show me 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This should be my output. Okay. So I want my numbers to be ordered in increasing order. Okay. I want my numbers to be sorted now. That is the problem statement that we want to design algorithms for. Yes, it is possible that we may want to like arrange them in decreasing order also. That is also included in sorting algorithms. But for that, you just have to like use wherever it's just you can just manage that, like we will be discussing the increasing order only, and you can just modify it to if you need it to solve the decreasing order problem. Okay, sorting in decreasing order. So now the thing is, for sorting algorithms there are multiple algorithms to sort a list of numbers. There are several algorithms. Okay, so we will be discussing only a couple of them here. So first of all, we'll look into what is called selection sort. Okay, so what selection sort does here is, see, this is a uh, video, I guess. This is there's a video. Okay, never mind, that video is not
Ma'am,
running.
Ma'am,
how you
need
have
to
to
click
click on
on the
that
sort.
sort?
Yes, ma'am.
Sorry?
You
You
have to
need to
click on
click.
that sort button there. Green one.
Okay, okay, this is going a little bit fast. Okay, let me just explain this. Okay. So what it does is, how do I stop this? Okay, yeah, fine. This is fine. So what the sorting algorithm, the selection sort algorithm does is it just scans through the entire list and finds the first, like the smallest element. Whatever is the smallest element in this entire list. So we'll start from this index, first index. Okay, and I will find whatever is the smallest element. Which one is the smallest element? 1 is my smallest element here. Right? So what I'll do is I'll just take this number, I will put it here, and I'll swap this 9 here. Okay. So then what will happen? My yeah.
Excuse
So
me,
now what
ma'am.
will happen is,
Excuse
yes.
me, ma'am. How the algorithm know that the number one is a minimum number?
Okay. So for that we can just look into this. Okay. Okay. I'll come to that. So what we will do is we'll just store this smallest number. We will have a variable, okay, that will store the index containing the smallest number. We'll start with the variable. Let's say I'm starting from the position 0, so I will call this variable is called your min cost. So this min cost will store 0 first. Okay. Then I go to 3. This will be kind of a linear search. Okay. We'll perform kind of a linear, somewhat a different modification of a linear search algorithm here. Okay. We'll go to the first index. We'll see that this position is having 3. The position containing min cost was having, which was 0, is containing 9. So I'll compare these two. Which one is smaller? 3 is smaller. So I update the value of min cost to contain store 1, which is basically the index of 3. Okay. Then I will go to the second index, and I see here that the value at the second index is less than the value at the index of min cost. Okay, so my main position is having the index 1, which is containing the value 3, and that value 3 is greater than 2, which and hence 3 is not the smallest value. right? 2 is the smallest value as of now, right? So I will update this min position to contain 2 instead of 1, okay? And I'll keep on doing that. Okay, once I have exhausted all the numbers, notice that whatever will be the value at this position, at this min pos variable, whatever will be the value, that will be the smallest number in this entire list of numbers. Is that clear?
Yes,
Yes,
ma'am.
ma'am.
So, ma'am, we can
Okay.
say that the comparisons will be high, but the swapping time is less.
Yeah. Uh,
Swapping is less, but
yeah.
the comparisons are high, right?
Yes, obviously, like we will be
Yeah.
performing the number of comparisons will be order of n squared. We'll come to that.
Yes.
Okay.
Okay.
So now my here I have one here. So the minimum index was in this position, the third position, and I was compare. I had started from the first position, right? So now I'm going to swap this two. Okay. So I have my 9 will come here and my 1 will come here. So I have 1, then 3, 2, and then 9, then 6, 4, 8, 10, 5, 7. Now, what I already know is my first position, my 1, is at its correct position. I know that 1 was supposed to be here. It was at the third position, but now I have put 1 at this position, which where it is supposed to belong. So the smallest index, smallest value in this entire list of numbers is in the first position. So I don't need to come back here, no matter what happens, because it is already in the correct position. So I will start from the second position. I'll just ignore the list from until this much, and I will repeat this entire procedure on this half of the list. Okay. So now in this part of the list, what is the smallest value? 2. So I will like I had started from this particular position. My smallest value is 2, which is at this particular index. So I will swap these two values. Okay. So, and then I will get 1, 2, 3, and then 9, 6, 4, 8, 10, 5, and 7. Okay, so now I know that my algorithm knows that these first two positions are correct, holding the correct values. So it need not look into that position again. Okay, but here, although 3 is at its correct position, my algorithm doesn't know that. It's just a machine. It doesn't know that 3 is in the correct position. So even though 3 is in the correct position here, it will start looking from this position on till the last. It will look into this entire half of the array, finding the minimum value among this part, not this part, not the entire list, but only in this part of the list, whatever is the smallest number, it will find that number and it will put in the first index of that half of the list. And this will be keep on repeating. And once you keep on doing this, at the end, the algorithm will give you a list which will be completely sorted in increasing order. Okay, so this is the selection sort. So in selection sort, what is happening? If we come to the running time complexity of the selection sort, what is happening here? We keep on comparing. So how many comparisons we will be performing? So the first time we will be performing n comparisons, right? With for every
Yes.
number, we will start with 9 and then we will compare every number with the value, whatever will be the min position value. So there will be n comparisons in the first time. In the second time, for this scenario, how many comparisons will be performed? N minus
N
1
minus
to
1.
be exact. Right. In the second one, we will be performing n minus 2
N
to be
minus 2.
exact. Okay. So, and this we will do for n times, right? This will be
Yes.
performed n times. And in the last one, there will be exactly one comparison. It will be probably n minus 1 or n, I don't exactly, yeah, it will be probably n minus 1 times. No, it will be n, the last one will be 0 or something. N minus 1, then it will be n, so it will be 0. Okay, 0 comparisons. or one comparison or something of that sort. Okay. So anyways, so the running time will be, so for the, it will be n plus n minus 1 plus n minus
Ma'am,
2.
for the first element, it will be n minus 1 comparisons, right?
Yes, ma'am. It should be n minus 1.
Yeah. It is n minus 1, this is n minus 2, this is n minus 3, and that is why it will come 0 here.
Yes.
Okay.
Ma'am, it should come 1 now.
We are going to n minus 1. The last value will be n minus 1 here.
Yes,
So
it
we
will be
will be
0.
having, this loop will not get executed. It will become n to n. No? So it will not get executed. So the number of comparisons will be 0 here. Okay. So this will go till 0. And if you find it, solve this, this will actually be order of n squared. Is this clear?
Yes, ma'am.
Okay, so now swapping is always unit amount of a constant time. Okay, so this will always be considered as constant time because swapping is basically a fixed number of operations. So that is why the swapping operation will always be considered as constant time. And when you exactly look into how many operations are being performed and look into the to compute the time complexity, you will realize that the time complexity is dominated by the number of comparison operations that are being performed. Okay, so since we are having order of n squared comparisons, the time complexity for selection sort is also equal to order of n squared. Okay, any
Yes, ma'am.
doubts? Okay,
How
if
it is
there are, sorry,
okay, how it is n square?
you can solve this. For the first time, it will be n minus 1. The second time, it
Ma'am,
will be n minus 2
ma'am,
and
it
so
will
on.
be n into n minus 1 by 2.
Yeah, n
It will
into
become
Yes,
a
n
that,
minus
series, yes.
n
that's
into
some
n
rule.
minus 1 by 2, right?
Yes, ma'am.
Yes,
So
ma'am.
this is
Last
equal to n 1 by 2 n squared minus 1 by 2 n. So this is order of n squared. Is this clear?
Yes, ma'am.
Yes, ma'am.
Any other doubts? Okay, if there are no doubts, then I'll go to the next shortening technique. Okay, so now we have insertion sort. What insertion sort is, so I believe if you have ever played cards, then you have performed insertion sort in your real life. Okay, so suppose you are having a bunch of cards and you are asked to sort them. So what you do, you find the smallest card and you push it backwards until you keep it in a position where it belongs to, right? So that is exactly what insertion sort does. Suppose we have, I'll go back to the list, which is, okay, I have 9, 3, 2, 1, 6, 5, 4, 10, 7. This was my list initially, suppose. And now what I am going to do is I'll start from 9. Okay. Before 9, there is nothing. Okay. So I'll just skip. I'll just go to the second iteration. What happens in the second iteration? I'll go to 3. 9, 3, 2, 1, 6, 5, 4, 10 and 7. Okay. So what happens is till this much it has been sorted. My array is sorted till this much. Okay. So now I am going to 3. So I pick the card which says 3 and I will put it in the position where it belongs to. So in this half of the array, where does 3 belong to? I'll find it. So I'll compare 3 with 9 and I see that 3 is less than 9. So my 3 should precede 9. Okay, so what I'll do is I'll just swap this two. Okay, what will happen now? I'll get 3, 9, 2, 1, 6, 5, 4, 10, and 7. Now notice that there is nothing before 3. So now this part of my array is already sorted. Whatever numbers are here, this has been sorted. So now suppose then what I do, I'll go to 2. I want to sort 2. Okay, I'll pick up the card which says 2. So what will I do? I'll find the position where 2 should go in this part of the list. Okay, so now 2, I will compare 2 with 9 and I realize that okay, 2 is less than 9. So 2 should come somewhere before 9 in this part of the list. So now, okay, so I will just swap this 2. My 9 will come here. I'll just erase or I'll use a different color. Let's say I'll use green here. So I'll just swap this 2 and I'll have 2 here, 9 will be here. And then what will happen? I'll see 2, compare 2 with 3. And I see that, okay, 2 is still less than 3. So 2 is not where it is supposed to be. So now what will happen? I'll just swap this 2 and
Hello, ma'am. Ma'am, you are not audible.
hello?
Yes, ma'am.
Okay, so there was a power cut because of which I got disconnected. So,
Okay.
can you please tell me until where I was there?
Ma'am, you were just telling we will check the before, I mean, previous element and then swap it. I mean, 2
Okay,
and 3
so
we'll check.
yeah, so we'll check between 2 and 3
Ma'am, your screen
and
is not visible.
oh, okay, 1 minute. Okay, is it visible now?
Yes, ma'am.
Okay, so we will check between 2 and 3 and we realize that 2 is less than 3. So we will swap 2 and 3 and we will have 2 here and 3 here. Okay, so now what happened is 2 and 3, both of them were now 2, now I will go to the previous element and I will check, but I realize that 2 is the first element now. There is nothing beforehand to compare with. So, which means that this part of my list has been now sorted. Okay, 2 is exactly where it's supposed to be. Then 3 and 9. So, this part of my list is like set. This part of my list has been sorted. Okay, so now let's go to the next element. So, there was one here, but I have removed one here, one from here. Okay, I removed one from here and I did not realize at that time that I got disconnected. So there was one, but I had erased it. Okay. So let's assume that my input did not have one at all. Okay. The reason is because it will again come to the first, which I have already demonstrated for both 3 and 2. Okay. So let's start with 6. We will start with 6 now. So let's suppose the next number in the list was 6. Okay. So now we will sort 6. What we will do is we will put 6 in the exact position where it was supposed to be uh, in this part of the list. Okay, because we know that this half of my list was already sorted, I will pick 6 and I will put where it is supposed to be in this part of the list. So what I'll do is I'll go to the green color. Okay, so I will take 6 and I'll compare 6 and 9. So now 6 is less than 9. So I will just swap this two. I will make sure that my list gets sorted until this part. So I will take 6 and I will fix this 2. Okay, I will swap this 2. So my 6 will come here and 9 will come here. Then I will take 6 and I will compare with 3 and I realize that okay, my 6 is at where it is supposed to be because 6 is greater than 3. So everything before 3, I already know that everything before 3 are less than 3 and my 6 is greater than 3. So my 6 will not go anywhere before 3. Okay. So I really compare 6 and 3 and I realize that 6 is okay, exactly where it is supposed to be. Okay. So now I realize that my list has now been shorted till this point. And whatever is there after that, which is 5, 4, 10 and 7, all of this part will be sorted after this, but this part of my list is short. Okay, and I keep on doing this until my entire list gets sorted. Is this clear? The insertion sort?
Yes, ma'am.
Okay, so now coming to the running time again. So if we look into the, this is the algorithm for the insertion sort. If we look into the running time, the worst case time complexity, what will be the worst case time complexity? The worst case time complexity will occur when my list is completely inverted. Like instead of having 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we are having 10, 9, 8, 7, 6, 5, 4, and so on. Okay, so my list is completely inverted. So every time I am picking up an element, I will be performing, like I will have to compare with every other element in the previous to that element. Okay, suppose I am picking an element at the first index. Okay, if I am picking the element at the first index, then there will be zero comparisons. If I am picking the element at the 1th index, then how many comparisons there will be? There will be
1.
one comparison. If I am picking the element at the 2nd index, okay, then how
2
many comparisons there will be? 2 comparisons. If I am picking then when I pick the element at the 3rd position, there will be 3 comparisons. Okay, and this will keep on repeating for the nth element, which will be basically the smallest element of the entire list. It is there in the last value, last position. So for that nth element, we will be having n minus 1 comparisons,
Yes.
right? So this will be
Yes, ma'am.
actually n minus 1 index, which is the nth element at n minus 1 index. Okay, so there will be n minus 1 comparisons. So what will be the total number of comparisons? The total number of comparisons will now be again be equal to order of n squared, right? Why? The number of comparisons will be 0 plus 1 plus 2 up to n minus 1, which will again be equal to n into n minus 1 by 2, which is actually order of n squared. So again, if you look into how many operations are being performed and all of that, you will realize that the total number of operations dominates the running time of the algorithm, and hence the running time complexity of this algorithm will be order of n squared. Okay, I hope that is clear.
Yes, ma'am.
Okay, so then we will go to the next one, which is merge sort. Merge sort is basically a little bit of smartly sorting kind of thing. So what it does is, suppose we have the same list 9, 3, 2, 1, 6, 5, 4, 10, 7.
Ma'am,
Okay.
just a second. For
Yes.
the insertion sort, the worst and best case will be same.
So no, the best case will be order of n for insertion sort.
Okay.
When will that best case occur for insertion sort? What will be the best
When
case?
all the elements are arranged already.
Exactly. When all the elements are already sorted, we will keep on comparing that element with its previous element. right? Every
Yes.
element at its position will just compare with its previous element, will realize that it is at its correct position, and will just go to the next position. So there will be n minus 1 comparisons.
Okay, ma'am.
Okay, so that is why the time complexity for the best case scenario for insertion sort will be order of n.
Okay, ma'am.
Yeah. For merge sort, what we will do is we'll just divide this entire list into two parts. Okay, and then we will short this half, we will short this half, and then we will merge. Somehow, let's say somebody says, okay, give me this half, I will short it for you. And some other person says, give me this half, I will sort it for you. And they give you this shorted list. Okay. So what will this come back? This will come to 1, 2, 3, 6, and 9. And this person gives you 4, 5, 8, sorry, 7, 8, and 10. Okay, so now what you have to do, I just have to merge these two. Okay, how will I merge? I'll see the first one, I'll take 1 and I'll see 4. 1 is less than 4, so 1 comes. Then I go to 2, 2 and 4, so 2 will be there. So then I compare with 3, 3 and 4, so 3 will be there. Then I go to 6, 6 and 4, 4 is the smaller one, so 4 will be here. Then I go to the next element, which is 5. I compare 5 with 6 and I realize 5 is the smaller one, so 5 will come next. Then I go to 6. I see 6 and sorry, I go to 7. So I compare 7 with 6 and I realize 6 is the smaller element, so 6 will come. Then I go to 9 and I compare 9 with 7 and I realize 7 is the smaller one, so 7 will be here. Then I go to 8. I compare 8 and 9 and I realize 8 is the smaller one, so 8 should come here. Then I go to 10 and I compare 9 and 10, and I realize 9 is the smaller one, so 9 should come here. And then finally 10 is just remaining, so I just write 10 here. Okay, so this is how I just sorted. I just combine these two shorted lists. This is what is called as the combining procedure. Okay, now this is the part where we are dividing this entire list into two parts. And then I am just sorting each of the halves independent of each other. Okay, so how do I sort these two halves? What I will do is this entire procedure is my merge sort. I will divide into two. I will ask somebody to sort these two, and then I will just combine them both. Okay, so now this is what is called as the merge sort. So now the question is, how do we sort each of these halves? So what I will do is, each of these half, I will again apply a merge sort. On this part, I will apply a merge sort. And again on this part, I will apply a merge sort. This is basically, I'm giving you a bunch of papers and I am asking you, sort all of these papers according to the roll numbers. So what you do is, you just divide into two parts. You ask your friend to help you out, sort one bundle, and you sort another bundle, and then you combine both of them. That is the idea behind the merge sorting. But what we are going to do here is we will be taking it a little bit more to the next step. And instead of just sorting one half each, we will find some two more people and we will give this, like whatever half I am having, I'll divide it into two and I'll give the other two people once again. Sort this for me, combine and give it to me. So now I am having a sorted order. Okay, so this is what the merge sort does. It recursively sorts half of the list. Okay, is this clear or do you have any doubts here?
Yes, ma'am, it is clear.
Okay, so now this is actually this is the visualization. This is the pseudo code. The merge is the merge function here, the combination function where we are merging these two shorted lists. This is what is in the merge function. And then there is the merge sort. What merge sort does is it just divides into two parts, divides the entire list into two halves, performs merge sort on each of these two halves of the list. Half of the list. The first half was from the 0th index to n by 2 minus 1th index, and the second half was from the n by 2th index till the last index. Okay, so we apply merge sort on each of these two halves of the list, And then finally we merge both of these halves using the merge function. Okay, this is what merge sort is. So now the question is, what is the running time complexity of this merge sort algorithm? Okay, so what happens again, because this is recursion, we will go with recurrence relations. So what will be the running time complexity? So let's say the time complexity on a list of n numbers will be T of n. Okay, let's say for the time taken by this merge sort function will be whatever on n numbers will be T of n. Then what happens? This will be unit constant time. So this is order of 1. This will be order of 1. Initially, we will not be executing this because obviously my n is not equal to 1 or it is not less than equal to 1. Okay. So we will go to this part wherein we are again applying merge sort on a half of the list, on a list containing n by 2 numbers. Okay. So what will be the running time for this part? This will again
T
be
of n
whatever
by
is exactly. Whatever is the running time complexity for merge sort on a list of n by 2 numbers. Okay. And then we have for the right half, we will again have, it is again we are applying merge sort on n by 2 numbers. So that means the time required to compute this particular statement will be equal to whatever is the time required by merge sort on n by 2 numbers.
yes.
Right? And then we have this particular statement, which is basically what? This is merging two lists containing n by 2 numbers. This is n by 2 numbers. This is n by 2 numbers. I am merging them together into one list containing n numbers. Right? So, whatever is the running time of this, what is the time taken to perform this merging operation? So, that we have to calculate here and that we will have to add here, right? That is the third part of this pseudocode. So, this will be some order of something we will calculate and we will put it here. And then this is order of 1. So, we have something order of 1 here and we can just ignore this, okay? So now what we will do is we will just calculate what is the time taken to perform this merge operation, right? So now can you tell me what exactly will be the time taken to perform this merge operation? What we are doing for both of these n by 2 plus n by 2 numbers, we are starting from the first numbers and I am comparing which number will come first, right? Whatever number is coming first, I am just putting it here and I am just skipping to the next number. Okay, and then I'm comparing this with the same number and I'm just putting it here. Whatever is the smaller one, I'm putting it here and then I'm just skipping to the next number. Right? Essentially, I will be performing n comparisons, order of n comparisons. Do you agree to that?
Yes, ma'am.
Okay, so when you look into the running time, the pseudocode of this merge sort, if you look into this entire pseudocode, you will realize that again the number of comparisons will be dominating the entire pseudocode, the function, and hence this part will be order of. Okay, so my time complexity, the recurrence relation will become 2 times t of n by 2 plus order of n.
Ma'am,
Yes.
ma'am, could you please repeat that order and the merge part?
Yes, I'll come back to that. Okay. So, what the merge thing is doing? I have a list of n by 2 numbers. I have a list of another n by 2 numbers. And what I'm going to do is I will create a list of n numbers, okay, in some particular order. So, what I do is I'll just start from the first indices. Hello?
Yes, ma'am.
Yeah, I'm connected, right? Okay.
Yes.
Okay, so I will start from the first two indices. I will compare these two indices and I'll see which of these two will go into the first index. Okay, let's say one of them is going into this particular value is going into the first index. I just put it here and I go to the next number, right?
Yes, ma'am.
Yes, ma'am.
Yeah. So now this I am comparing with this number again, and I see that okay, this number is coming here, so I cut it from here and I put it here, and I am going to the next part. Okay, I keep on doing this until all of these n by 2 values come here, all of these n by 2 values come. So what will be the maximum number of comparisons that you will be performing? For every particular number that you are putting it here, you are performing exactly one comparison, right? Do
Yes,
you agree? Now you are putting n numbers in this list. That means for every number, because you are comparing, like performing exactly one comparison for every number, which means if you are creating this list of n numbers, the maximum number of comparisons that you will be performing will be order of n. Do you agree to this?
yes, ma'am.
Yes, ma'am.
Exactly. That is why when you look into the pseudocode of this merge sort, all it is doing is it is just going from one index to here until n by 2, and from one index to this last index by 1 by for this n by 2 numbers, and it is just copy pasting whichever is the smallest index between whatever the two numbers it is comparing, right? So essentially, the number of comparisons will dominate the total running time of the merge function. Okay, is this clear or doubts?
No, ma'am. Clear.
Okay, so the running time of the merge function will be order of n. Okay.
Yes, ma'am.
Okay. So now in this merge sort pseudocode, if you look into the pseudocode for merge sort, we have the left half is going from, first of all, we perform a merge sort on for the n by 2 numbers, the left n by 2 numbers, which is giving me a running time of t of n by 2, this first t of n by 2. The second part is merge sort of L of n by 2, which is the last n by 2 numbers. So it will give me whatever, it will give me the number of comparisons that you will be performing for this particular number. Okay. So when we are performing a merge function on two n by 2 lists, two lists of n by containing n by 2 numbers, and I am merging them,
Ma'am, your voice is breaking in between.
okay. So when I solve this t of n by 2 plus t of n by 2 gives me 2t of n by 2 plus this order of n. Is this clear?
Yes, ma'am.
Okay. So then we have, when we solve this actually, if we keep on going this, so what will happen here is if I keep on solving this, this will become 2 times 2t n by uh, n by 2 by 2. Okay. So n by 2 square, which is n by 4, plus order of n by 2 whole plus order of n. Is this clear? Do you agree to this?
Yes, ma'am.
This comes from
Yes.
here. Okay. So now this will be equal to 2 squared times t of n by 2 squared plus order of n by 2 plus order of n. Okay. So now this will again become 2 squared times 2t n by 2 squared by 2, which will be 2 cubed. Okay. Plus order of n by 2 squared plus order of n by 2 plus order of n. Okay. This will become 2 cube times t of n by 2 cube plus order of n by 2 squared plus order of n by 2 plus order of n. Okay. And when you keep on doing this, at the last you will get order of n plus order of n by 2 plus order of n by 2 squared up to order of n by 2 to the power log n or something, which will actually become equal to 1. Okay, so this will actually be, if you solve this geometric progression, you will realize this will be order of n times log n. Okay,
Okay, ma'am.
any doubts till now?
Well, could you please repeat the last part after this?
After? Hello?
No, after writing this O of n plus O of n by 2 plus
Yeah,
O
this
of
is,
n by 2 log n.
yeah, this is basically, see, what will happen is, let me just erase this part. Okay, so what happens is when you keep on solving this, this will become order of n plus order of n by 2 plus order of n by 2 squared plus order of n by 2 cube plus order of n by 2 to the power 4 and so on, right? And the last one will be order of n by 2 to the power log n. Okay, so why this will be the last? Because this value n over 2 to the power log n is actually equal to 1. Okay, hello?
Yes.
Yes, ma'am.
Yeah, so now order of 1 is basically a constant and you have to halt them. Okay, so this is basically why we are stopping at this particular position. So now when you look into this equations, order of n, this will actually be equal to what? Order of n plus n by 2 plus n by 2 squared plus n by 2 cube up to n over 2 to the power log n, right? Do you agree to this?
Yes.
Yes.
Yeah. So now this is basically equal to what? Order of, this is basically a geometric progression. So you take n common and it will be 1 plus 1 by 2 plus 1 by 2 squared and so on. It's basically the sum of a geometric progression with r is equal to 1 by 2, a is equal to 1 and the number of values is log n. Okay, so when you solve this geometric progression, it will become yeah. So when you solve this geometric progression, it will be order of n times. This is 1 into 1 minus 1 by 2 to the power log n, I guess. This will be 1 minus 1 by 2 and this will be, do you remember the formula?
No, ma'am.
Yeah, there was some formula. No? Let's see. Okay, whatever, you can just try it out. And otherwise, if you're not able to solve this, you can just post on Discord. I'll solve it and send it to you. Okay. So this will actually reduce to, this part will come log n. Okay. If you solve this, okay, some constant times log n, maybe 2 times log n or something, which will essentially reduce to order of n times log n. Okay. Hello.
Yes, ma'am. It's clear.
Okay. Okay, then let's see what else is there. So, actually, for the interesting thing is for merge sort, both for best case and worst case and average case, for every scenario, merge sort will take order of n log n time. Okay. as unlike the other sorting techniques which we have seen till now, which is the selection sort and insertion sort, the best case time complexity was order of 1. Here, best case and worst case have the same time complexity, which is order of n log. Okay. So apart from that, this is just basically some functions, and these are some dictionary methods. Time complexities are given here.
Do we have to remember
Which
this?
not really. You don't really need to remember every one of them, but in case if it is required in future weeks, then you may have to come back and just refer it how much time it is taking.
Okay, ma'am.
Okay, yes. You don't have to like wrote all of this. Okay, no need to learn all of this. You just have to look
Okay.
into what it is.
Okay, ma'am.
Okay. If you have any doubts, then I can clear it. Otherwise, we can end the meeting.
What is this amortized?
Amortized is actually a whole different scenario, but I'm not sure if we will be covering amortized complexity in this course. So you don't have to make it.
Ma'am, I have one question. Ma'am, what is good in general? What is good to have a less swapping time or less comparison?
Swapping time is always the order of 1. No matter what happens, swapping time will always be order of 1. Okay, so see, what you can do is how many times you are either your algorithm, either it will be dominated by the number of comparisons or by the number of swapping operations, or both of them will be equal. Okay, there are just these two things that you need to see. How many swapping operations are being performed? How many comparisons are being performed? Either one of them will be dominating your algorithm. But the thing is, comparison operation, the less than equal to or greater than equal to that you are seeing. A is less than equal to B. This operation is order of 1. See, now I have A comma B is equal to B comma A, the swapping operation. This is equal order of 1. Okay, so now whatever, now suppose this is having some order of f of n times uh, order of f of times and performing this operation, this comparison operation, then this will become order, this total running time for this particular operation will be performed order of f of n. Right? Now, similarly, the number of comparisons, number of swapping operations is suppose g of n. Okay, then I will be having the total time to perform this swapping operation will be order of g of n. And all you have to do is compare between these two. So instead of doing all of this entire thing, you can just see that because this is constant time, all you have to do is compare between the number of swapping operations and number of comparison operations. Am I making sense?
So there is no general thumb rule that one is better than another.
No, no. All we care about is my algorithm should take less amount of time. That's all is what I care about. Okay. So whether you optimize the swapping operation or whether you optimize the comparison operation, I don't care about it because both of them take constant time. Both of them are taking order of 1 time. So I don't really care whether you optimize the swapping operation or whether you are optimizing the comparison operation.
Okay, ma'am.
Is that clear?
Yes, ma'am.
Ma'am, usually order of n square is not better than order of n log n, right?
No,
Is,
order of n log n is better. Yes.
yes. So, ma'am, then why can't we say that merge sort is better than selection sort?
What if your list is already sorted and you are performing
So
master?
let's take the worst case for both the case. I'm
Yeah,
asking.
worst case, yes, for both the case, merge sort is better than selection sort. But
Okay.
there is a demerit in merge sort. It's that you need some extra list variables to store. So the storage capacity required for merge sort is more as compared to selection sort.
Yeah, we
Okay,
haven't covered the
so
space complexity, right?
Yeah,
It's
so
not.
space complexity is basically how much space you are requiring. It's nothing really big. It's very similar to time complexity. All that with space complexity is we just analyze how much space is required instead of how much time is required. And we will not be covering space complexity in this course. Okay, so it's
Okay.
nothing like anything extra is there. It is very similar to time complexity. It is exactly equal to time complexity. Just like instead of number of comparison operations or number of operations we are calculating for time complexity, in space complexity we will just compare what is the space required by every variable in every sentence. That's all.
Okay, ma'am.
And yeah, it is true that in the worst case, merge sort performs significantly better than every other sort, like most of the other sorting algorithms. So that is why if you look into sorting algorithms, like packages of Python or any other packages, already implemented packages, most of them will be having some kind of a modified and improved version of merge sort. It is a stable sort. It is it is fixed that you know that whatever you like in under any scenario your running time complexity will be order of n log n and so on. Okay, so merge sort is definitely better than selection sort for a average case scenario or for a worst case scenario, but for best case scenarios selection sort is definitely better than merge sort. Okay.
And even for the average, also we can say that merge sort is better for
Yes.
average.
Yes.
Okay.
And yeah, there is one more thing about stable sorting that I have not covered. This is nothing like nothing but what happens is suppose in your list one number is repeated two times. Okay, let's say my 6 is repeated or 7 is repeated two times. Okay, and when I'm sorting, what I will do is I'll just label this. Okay, this is the first occurrence of 7, so I will just label it as 8, and this is the second occurrence of 7, so I'll label it as D. Okay, so in my output, if this 7, the 7 with the label A occurs before the 7 with the label B, okay, this is A and this is B, then such a sorting technique is called as merge sort. Okay, but if
Stable sort, ma'am.
sorry, stable sort. Okay, but if my 7b occurs before 7a or something else, like suppose I have a c here also or and d. Okay, if it occurs in exactly this order, like first there will be A, then there will be B, then there is C, and then there is D, then we will say that it is a stable sort. But if any other order, like B occurs first and then A, B, A, C, D, or C, A, B, D, any other order, okay, any other order, if after sorting my sevens doesn't occur in this particular order, then we will say that the sorting technique is not stable. Okay, merge sort is
Yes, ma'am.
sort, selection sort is not stable. Okay, insertion sort is stable.
Okay, ma'am.
Merge sort is stable.
Sorry,
No, merge sort is stable or unstable.
merge sort is stable. Actually, for selection sort, you can have some
Yeah.
like you can do some things like in the min while you are checking for the minimum values. No, here, if you update it in a way that like probably for this particular implementation of selection sort, it will be stable or something. Okay. So if you
Yes, if
check
we
that, if it, yeah, for this particular implementation, it will be stable sort.
yes, ma'am. Using
But
less than equal to will make it unstable,
make
right?
it unstable. Exactly. Yeah. If you have less than equal to here, then the sort will become unstable. Similarly, for insertion sort also, If you have less than equal to here, it will become unstable. Here, if you have less than
Yes.
equal to instead of this less than, then it will become unstable. But for this particular implementation, it is stable. Okay.
Okay, ma'am.
Okay. Any other doubts? Okay then. If there are no doubts, then we can stop the meeting.
So to summarize, order of a function is the worst case time,
Yes, order of a function is the worst case time.
and omega is the best case.
Yes.
Excuse me, ma'am.
Yes.
Ma'am, could you please again explain the in place thing of?
Okay. So, mm, okay, so let's say there are two Rahuls in your class. Okay, so one Rahul is having the roll number is something 7, and another Rahul is having a roll number of 16. Okay, so then what is happen is, suppose I am sorting it. The first Rahul is coming first in your sort, and like the Rahul with the number 7 is coming first, and the Rahul with the number 16 is coming after that, then your sort is stable. Okay, what I mean is, let's say there are two Rahul are joining. Okay, one Rahul joined in the 7th number, so his admission number is 7. The other Rahul has an admission number of 16, so that Rahul has joined after this first Rahul. So now when you are sorting it, if the first Rahul with the admission number 7 is occurring first, and the second Rahul with the admission number 16 is occurring after the first Rahul, the after the Rahul with admission number 7. Okay, the second one, it is occurring as second number, second person. Then it is a stable sort. Okay, but if it is occurring in any other order, like the 16th one, the one with the number admission number 16 is occurring first, and the one with the admission number 7 is occurring after that, then it is not a stable sort. Is that clear, or should I give another example?
Ma'am, what is the difference between stable and in place?
Oh, okay. This is table sort. In-place sorting is basically, see, in merge sort, what happens when we are merging, we are just copying the entire list into another list, right?
Yes, ma'am.
So what happened here is we have not changed the original list, rather we are creating another list which is containing the sorted list, right?
Yes, ma'am.
So it is not an in-place sorting. But go to insertion sort or selection sort. What happens? We are given a list, and there itself, within on that list only, we are just swapping some of the values. We are manipulating that original list. We are just modifying the original list, and we are sorting the entire list. Right? We are not creating any other list. We are just sorting it in there itself. Right?
Okay, ma'am. Yes, ma'am.
So that is called in-place sorting. In-place sorting means you are not creating anything extra. Any other new variables is not required. You are just going to sort wherever it is, whatever it is in that place on the input list, whatever is given to you. There itself, you are just sorting it. You are not creating another variable to sort. You are not going to occupy any extra space. Okay, whatever is given to you on the list itself, on the list, in the list variable, whatever is the input list variable, you just keep sorting on that in that list itself directly, then it is called stable sort. Sorry, so that then it is called in place sorting. But if you need an extra extra list, just like in merge sort, when we were performing merge sorting operation, we created another list called merge sort, and we like this new list contained the sorted order. right? And then it was not, the sorted order was not there on the original list. Rather, it was a new list containing this new sorted order, right? So that is why it is not an in-place sorting. In-place sorting means we will just sort it there itself. You're not going to move around.
Like we are creating smaller lists, right? Merge sort, new lists.
Actually, if you look into the pseudocode, the new lists are constructed in the merge operation.
Okay.
Hello? Yeah.
Ma'am, for the merge sort case, can we consider that as the tight bound one?
Sorry?
Ma'am, we read about upper bound, lower bound, and tight bound. So the merge sort case is the one that corresponds to the tight bound condition.
Yeah, we can say that merge sort is tightly bounded by n log n. Yes.
Okay, ma'am.
Excuse me, ma'am.
Yes. Yeah.
Whenever we will be asked questions about time complexity, they will be mostly on the worst case.
Exactly. Yeah.
Okay, ma'am. Thank you.
Okay.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you.